We're going to practice this with an example. I have a bucket and I have 1 kilogram of water, and I'm going to swing this bucket in a vertical circle. Okay? And what we're going to do is we're going to calculate the force by the bucket on the water at the top and at the bottom. This is very similar to the problems that you have assigned for homework, and you'll have at least one of these problems on the midterm. So, there's the bucket, there's the water. Now, if we draw a free body diagram when the bucket's at the top, there's a weight force, and that's going to be the mass times G. What else? Well, there's no magnets, so what touches the water? The bucket. Does the bucket push or pull? Well, it's not a rope, it's not a thread, it's not a chain. It pushes. Now, whenever one thing pushes on another, there will always be a normal force. Now, this is a little bit complicated because the sides of the bucket are pushing in perpendicular to the sides. But I think we can convince ourselves that those are going to cancel out. It's only the force by the bottom of the bucket that's going to give me a net force on the water. Now, since the bottom of the bucket is above the water, that force is going to push the water down. And that's my free body diagram. Now, when I look at that diagram, that screams down. And that begs the question, if the acceleration of the water is down and the water's above Greg's head, why doesn't it just fall down on Greg's head? Yeah, why? Yeah, why? That's what we wanted to happen. Brave soul, why? Yes?
Because the bucket is, well, it's the same thing with the ride. It's constantly moving around.
Right. If the water were stopped up there, an acceleration down would say speed up in that direction. But if the water is moving, and it's moving at a fairly rapid rate, tangent to the circle, an acceleration down, which is perpendicular, is just going to change the direction of the velocity vector. It's going to make it go in that circle. Okay? Now, let's calculate how big that acceleration is. Now, we've got to do some approximating. We have this formula, v squared over r. Let's just, for the sake of making the numbers easy, take the r equal 1 meter. And that seems reasonable given the fact that I'm swinging it. So about 1 meter. Okay? Now, we need to find v. So let's assume that we swing that around once every second. In other words, I go 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000, 6 1,000. Okay? So, given that I have a 1 second time of going around, and I have a radius of 1 meter, what would the speed be? Well, I already accidentally showed you the answer, so let's put it back up there. It goes around the circle 2 pi r, where r is 1, in a time of 1 second. So if r is 1 and time is 1, that means the velocity is 2 pi, or 6.28, about 6 meters per second. Now if I put that into the formula up there with the radius being 1, I get 36 meters per second squared. Now before we stop, let's ask ourselves this important question. What is the total acceleration of the water? Is it the centripetal acceleration, 36 meters per second squared? Or do I have to take that centripetal acceleration and add gravitational acceleration? So I'd have 36 plus 10, or 46. Which is it? Tell me with your clicker. Okay, last call. Oh, we're not sure. But at least no one voted for E this time. Good, progress. Okay. Now, folks, the answer is 36. And here's the reasoning. When we were looking at acceleration, we used the operational definition of acceleration. And that operational definition is, how much does your velocity vector change in 1 second? And so what I did is I looked at the velocity and then the velocity 1 second later. I saw how different they were. That change, since it happened in 1 second, was the acceleration. Now, at no time during that derivation did I care whether that was a horizontal circle like a racetrack or a vertical circle like a loop-de-loop at the carnival. It doesn't matter. A change in the velocity vector is a change in velocity vector. And by Galileo's derivation, it's v squared over r. Now, if I look at that acceleration, part of it is caused by this normal force by the bucket pushing down, and part of it is caused by the weight. It's the net, or the total force, that causes this acceleration. So it's part of each. But the acceleration is just the v squared over r. Now, the net force, if I've got 1 kilogram of water, is 1 times 36, or 36 newtons. The weight of 1 kilogram of water is 10 newtons. So what's wrong with this diagram? What's the mistake there? How big should this normal force be? Yeah, it should be 26 newtons. It should be clear down to here. But we couldn't afford the bigger screen, and so we had to go with the mistake. Sorry. Now, what if I swing it slower and slower and slower? What happens to that acceleration vector? Gets smaller. And what has to happen to my free body diagram? Does this weight force change? Diet or exercise. And so that means in order for this diagram to screen less down, the normal force has to get smaller. And when that normal force goes to 0, the water leaves the bucket. So let's go slower and slower. Okay. 1 1,000, 2 1,000. Let's go slower and slower and slower and slower. I've got sponges in here, people. I took you for a ride. Okay. Years ago, we didn't have the sponges. We had this special powder, and you'd put it in there, and when you poured the water in there, it would cause the powder would cause the water to just go to a stiff, kind of like Jello jiggler sort of thing. And when Mark Baldwin, our demo guy, retired, we hired Jerry, and the first lecture I did that with, he said, "How much powder do I put in?" I don't know, Mark always did. So we didn't put enough in. And so I got this over my head and just Jello all over. It was disgusting. Disgusting. Now, let's look at the bottom of the circle. Okay, watch how clever the PowerPoint is. Oh, yeah. Okay. Wonderful. Now, the free body diagram, I still have weight down. The bottom of the bucket is now below the water, so it's pushing up. And my acceleration is going in which direction? Up. And so what's wrong with that diagram? Yeah, it's got to scream up. Okay? So let's see how much it has to scream up. The acceleration is still going to be v squared over r. If I'm still going that once a second, that's still going to be 36 meters per second per second. That means the net force is still going to be 36 newtons. But now it's 36 newtons up. The weight force is still 10 newtons. How big does that normal force have to be now? 46 newtons. 46 newtons. Okay? Excellent. We're a little bit early, but we're out of material. Have a great weekend. We'll pick this up on Monday.